So basically, the cylindrical and spherical, they're highly related. They're highly related to the polar coordinates in 2D. So let's quickly recall what that looks like. Recall polar coordinates. Basically, in the XY plane, we have just the translation from the XY plane to the theta plane. Okay. So we have x equal to r cosine theta, and y equals to r sine theta. And basically, the way that we calculate, translate the variable is that x squared plus y squared equals to r squared. And then, as long as you know x and y, you will be able to solve for r. And you usually will have r non-negative. And then we will be given sine theta and cosine theta as the ratios between x, y, and r, right? So then we will calculate the angle theta. Okay. So here we talk about the cylindrical coordinates. It's going to be direct extension. So basically, there'll be x, y, z coordinates in the three-dimensional space, but we just translate x and y. Okay, we just keep z the same. Okay, so in Calc 3, cylindrical coordinates, we just have x equal to r cosine theta, y equal to r sine theta. So once again, x squared plus y squared equal to r squared. So this is the important relationship. Z just stays as z. Okay, so we don't touch the z coordinate. So you can see here, basically the z coordinate or the elevation coordinate will not change, but basically if you do the projection of the point x, y, z down to the x, y plane, then you will describe that projection as a polar coordinates. So that's what we do. Okay. Therefore, if we have a solid E that's described, let's say, in type 1, in the sense that we have xy pair within some region D, and then it's cut between functions u1 of xy and u2 of xy as two surfaces bounding the z value. And by chance that this region D is described in terms of the polar coordinates. Okay. So here, D, we can describe it in terms of r and theta, such that, for example, we have theta cut between some specific angles, and then r is cut between two functions in terms of theta. Then we can describe these two integral over the solid E in a different way. Okay. So you notice that here, basically, we have z cut between u1 and u2, then rely on x and y, but eventually they will rely on theta and r. Okay? And then, so the region D now is described in terms of r and theta. So we just need to take these into consideration. The triple integral over the solid E of function f of x, y, z, dv. Basically, once again, we just translate x and y accordingly, right? And then we just need to notice that here for dv is going to be dA times dz. Okay, so dA, there's a formula for that. So let's just describe it. So for the outer intervals, it's gonna be in terms of r and theta for that region. So so here we have theta between alpha and beta. Okay, so we keep it there. R is in the middle, so it's gonna be h1 of theta, h2 of theta for the bounds. And here we just need to make sure that we have r dr d theta, so that represents that dA, right? The way that you calculate the region D, right? The area. And then we just put down Z. So Z is gonna come between U1 and U2. But now, since we don't have XY anymore, so XY will be translated into R and theta. So that's the polar substitution that we need to utilize. So this is R cosine theta, that's replacing X. R sine theta, that's replacing Y. Right? And for the upper bound, it's the same. So R cosine theta, R sine theta, that we need to substitute. Okay. And then we put down the Z and the most inner part. So you can think about this as a bracket that's just enclosing the Z component at the most inner integral in terms of Z. And here you can expect that when we are writing that function f of x, y, z that we are integrating, we still need to translate that x and y. Okay, so this is going to be r cosine theta in place of x, r sine theta in terms of y. And z we don't touch. So here, that r dr d theta is going to be important, especially this this r in the middle. So let's put it in red as well. So this r here is important. So basically, you see that we just translated from x, y, z to r cosine theta, r sine theta, right? Okay, so that's cylindrical coordinates. So it is as a combination of polar coordinates and the elevation coordinate, z coordinate. Okay. Example. So let's compute or we'll evaluate the triple integral. So let's say from -2 for x, and then for y is going to be between the radicals 4 minus x squared. Well, the negative of that and the positive. And finally, this is y. Yeah, I do need a little more space. But z is cut between the square root of x squared plus y squared and 2. See? And then we're integrating x squared plus y squared. Now the space is a little bit too much, but now you get the triple integral. So basically, we do see kind of like a hint. So basically, for the region here, you can see okay, x value is cut between -2 and 2. My y value is cut between these two square roots, and it seems like it relates to a circle, right? And then also we notice that the most inner integral we have the sum of x squared plus y squared under the radical. Okay, so this is sort of hint that if you utilize the polar coordinates in terms of x and y, it's going to be nice. Okay, so let's translate the xy coordinates. Okay. So here we're gonna translate x and y so that we will describe a region D in terms of the xy plane, and it's gonna be the way that you subdivide the region into pieces, that's gonna be dA. Okay. And for the most inner integral, we just still is copy that down. So it's from the square root and all the way to 2, and then we're integrating x squared plus y squared dz. Okay. But now we need to describe that region D. Okay, here where this D is, so basically we just realize that the upper bounding and lower bounding function in terms of y is going to be square root of x minus 4 minus x squared. So we'll square both sides, we will have y squared equal to 4 minus x squared. Okay. So that's indeed a circle. So our region D is something like this. And x is coming between negative 2 and 2. And we have the boundary to be x squared plus y squared is 4. So indeed, the upper bounding function is the upper semicircle, and the lower bounding function in terms of x is the lower semicircle. And then, of course, for this kind of circle, we have a radius of 2, and then the center is the origin. So for polar coordinates, it's actually really straightforward, right? So basically, just saying my theta is 1 period, so it's let's say between 0 and 2 pi, right? And r is going to be between 0 and 2. Okay? So we can directly translate the region D now in terms of r and theta. And this is a polar rectangle, so the order doesn't matter that much. So we can put the theta down, it's going to be from 0 to 2 pi d theta. So r is between 0 and 2, dr d theta, we'll keep it there. So that's in place of d and dA. Okay, region D and the way that we subdivide. And now we play with the inner part. Okay. So now the inner part, we have what? We have x squared plus y squared equal to r squared. Okay. So that's in place of x squared plus y squared, sum of squares. We still copy down dz. And then for the lower upper bounds, so we realize that under the square root, r squared just gives you r back, right? So here we have non-negative r values. So it's good. So here you see that this is the polar coordinates that we do right here, so that the radicals are all gone. Okay. And then it will be not so hard to just compute. So for the most inner part, we just have, okay, so you're integrating z, but then r squared is treated as a constant. So that the inner integral will be that the r squared as a constant multiplying by the length of the integral, right? Of the interval from r to 2. So here for the outer, we keep the things down, d theta. And then we have on the inner, we have r squared times 2 minus r. Okay. So now we see, okay, we have a polynomial function from the inner, which is a degree 3 polynomial. And then on the outside, we are multiplying r again. Okay. And we also realize that the whole function that we're integrating is in terms of r. Okay. So if we separate this integrand into 2 functions multiplied in terms of r and theta respectively, then for the theta part is actually 1. Right? So this equals to 2 pi. So if you just integrate from 0 to 2 pi d theta, that's just 2 pi. Then multiplying by the integral terms of, so this is actually r cubed, 2 minus here. So that's just as long as we can separate the functions, we can separate the w integral into single definite integrals, times r theta. And then finally, we just need to do the antiderivative. And so this is actually, so this function is 2r cubed minus r to 4. Right? So if we want to write down the antiderivative, so now these are individual monomials. Okay? So it's going to be at 1 divided for both terms. So it's going to be 1/2 r to 4 minus 1/5 r to 5. And whenever you write down the antiderivative, always this differentiate and check. And so it's going to be 1/2 times 4 times r cubed minus 1/5 times 5 times 4. That's good. So we plug in r equal to 0 and r equal to 2. So essentially, you should get 2 pi times 8 minus 32/5. 14 minus 0. So this is essentially 16 pi over 5. Any questions so far? So in this example, you see the power of cylindrical coordinates, right? So basically, for radical isomorphism x squared and y squared, this is the sort of a hint. Okay? And so in terms of x and y, it seems like the region in the xy plane is going to be a circle. Okay? So that's another reason that we do this translation. Right. So cylindrical, basically that's relatively speaking straightforward. So now let's look at the spherical coordinates, which is a little bit more involved. So just be reminded that for the cylindrical coordinates, we only translate x and y coordinates. Okay, so instead of using x and y, we use r, distance from that point to the z-axis, right? And then the angle within the xy plane about the rotation, and finally the z value, the z coordinate will not change. So, but sometimes it does not really help you solve the triple integral. So let's look at a motivating example, which we will solve after we completely establish the spherical coordinates. Okay? And now let's say we are integrating over a solid E of this function. Okay, so here we have E to the exponent of x squared plus y squared plus z squared, whole thing raised to 3/2. And then dv. And here, E is special in the sense that this is a ball. Center, this is a unit ball, okay? Centered at the origin and has a radius 1. So we follow the tuple such that the distance from the point to the origin is upper bounded by 1. Okay. So here we just, so the left-hand side is the distance squared, right, from the origin to the point. It's upper bounded by 1. So indeed, this is exactly the ball enclosed by the unit sphere. So if we want to quickly sketch what the solid is like, it's going to be. So the cross section in the XY plane is exactly the unit circle. Right, so now let's quickly look at the iterated integrals that we can write out given the XYZ coordinates or the cylindrical coordinates. So in either case, we should describe that intersection within the XY plane, right? So basically, you have a sphere, okay, you have a ball actually, and then the first step that you do is you want to project onto the XY plane, and in this case, it's the intersection. And so this is actually that unit disk, right? That's that region. So in rectangular coordinates, what we're gonna get is, so basically to describe that unit circle is gonna be -1 to 1. So let's say we use dx on the most outer side. And then for y, it's gonna be between the radicals, 1 minus x squared under the square root, y. And finally, so here, by solving the z coordinate, okay, here we have the upper bounding hemisphere and the lower bounding hemisphere that's solved from this equation, okay, x squared plus y squared plus z squared equals 1. We solve for the z value, there will be two radicals again. So it's gonna be the square root of 1 minus x squared minus y squared, and the negative of that is e. Okay. And finally, so here we don't really change anything to the function. So it's still e to the sum of squares to the 3/2. Okay. So this integral is definitely hard to integrate in the sense that firstly, so for the most inner part, we're integrating in terms of z, but okay, we don't really know the anti-derivative for this in terms of z, right? And secondly, okay, we see a bunch of radicals. So here we have a radical, and here we have a radical. So XYZ is definitely hard. Okay, so if we do this coordinate, and now, of course, it's tempting to translate the things in terms of the cylindrical, because we know, okay, so at least we can rewrite the outer integrals in terms of x and y. Okay, we translate it into r and theta, so that will be definitely a little bit easier. So in cylindrical coordinates, so let's write the things together. So basically, that region D is the unit circle. So once again, we just have a polar rectangle, right? So theta is between 0 and 2 pi, and r is between 0 and 1. So we can write that down. And now, let's do this systematically. So we just keep in mind that we have r d theta at the end. Okay. So now we have x squared plus y squared is r squared, right? So we can do that translation under the radical for the most inner part as well. So 1 minus r squared under the square root. Okay. And then for the inner function, we have x squared plus y squared equals r squared again. So r squared plus z squared to the 3/2. And then here for the cylindrical coordinates, we just have r dz dr d theta. So here we just translate x and y all in terms of r and theta. So it's definitely a little bit simpler than the XYZ coordinates, right? But still, for that integral in terms of z in the most inner part, we still don't really know how to write down the antiderivative. Because essentially in terms of z is the same thing, right? It's e to the constant plus z squared whole thing to the 300. Okay? So that's the first challenge. And second of all, we see that we still have a radical here in terms of r. Okay? So without going deep into the integration, we can see that both integrated integrals are cubed. So definitely here, one thing that we want to motivate is that, okay, so when we talk about the polar, we want to translate the sum of squares x squared plus y squared under a radical, right? Here we have x squared plus y squared plus z squared under a radical also. So this is to the 3/2. So if we are able to translate the sum of squares, and we know that this is actually a distance from the point to the origin, right? So if we are able to utilize the distance from the point to the origin as one of the features, and then we utilize, okay. So that will definitely help you for that radical part. Okay? And here comes that coordinate description. Okay? Spherical coordinate system. So keep in mind, we just want one distance, but we introduce one more angle. Okay? So let's say this is the point P in the three-dimensional space. Let's also write down the x, y, z axes first. Okay? So let's say the coordinates are x, y, and z in the rectangular coordinates. And now here we want to do this. We want to identify the distance from the origin to the point. So that we will call as rho. Okay. And now, so it's a little bit different from the cylindrical. So let's firstly quickly do the cylindrical. So just be reminded what cylindrical does. So for x, y, and z, we only translate x and y, right? We don't really do anything to z. So that just means what? That just means we project this point P down to the xy plane, and then we decide there's an r and a theta, right? So let's quickly do that in the figure. So projection down to, let's say this is the point P prime. So that projection is exactly what? It's exactly x, y, and 0, right? And then, how do you decide that theta angle? So theta is actually in the xy plane. You decide, okay, this is r, the distance from P prime to the origin within the xy plane, right? And then theta used to be the direction x rotates to the direction of O P prime. What's going to be the rotation angle, right? So that's theta. So here, well, if you do that, then cylindrical becomes r cosine theta, r sine theta, z, right? And for the projection point, it's going to be P prime, which is r cosine theta, 0. Right? So Basically here, when we calculate these trig identities, so you see that for this point P prime, if we draw the projection onto the x-axis orthogonally, and we draw this projection down to the y-axis orthogonally. So you see that basically the x value is this segment, right? The y value, let me put it in black. So this is the x value, and this is the y value, right? So the y value is what? The y value is the opposite edge that's within the triangle, where the hypotenuse is half, right? So this is y is r sine theta, and then x is the adjacent edge. So this is our cosine theta, right? Okay, so now, so that's the cylindrical coordinates, right? But here, instead of using r theta and z, we're gonna use this rho, okay? And we also introduce another angle. So angle here that we're gonna introduce is this rotation angle, which we call phi. Okay, so this is the rotation angle from the z-axis to the direction OP. Okay, so let's write the things down. Spherical rho theta phi coordinate system. So firstly, we decide what rho is. Rho is the distance which is the magnitude of the vector OP. Okay, so this is definitely always negative. And the second thing that we can observe is just really similar to the cylindrical coordinates and the polar. So basically, here we do the projection down to the xy plane so that we only have x and y, and then we decide that theta. Okay. So theta is the angle of rotation from positive x-axis to the direction OP prime, where P prime is the projection of cap P on the xy plane. So here, this is the same theta as in cylindrical coordinate systems. Cylindrical coordinate system. And also we specify that R in that system is non-negative and theta, so it's the same to have one period. So let's say between 0 and 3. And finally, we have so the only thing new is that phi. Okay. And as we describe, phi is angle of rotation from now positive z-axis to the direction OP. So, so this is exactly as we described in the figure, right? So let's quickly look back. So exactly what does it do? So basically here, as long as we decide P prime, so we want to describe this point P, but we don't really want the XYZ coordinates, right? So here, if you do the projection down to the XY plane, as long as you have that theta, you will be able to somehow set up this plane that's within the vertical, which is perpendicular to the XY plane. So this is the plane that you directly decide if you have the angle theta, okay? And now here, we just need to notice that for this point P, it will be definitely within the upper half plane. So basically, so we have this direction z right here, which is all the way up, right? And we have this direction that's decided from the angle theta. Okay, so these two axes will form you a coordinate system. But then, if you want to decide the direction OP, then you just need to do another rotation. So here we decide to rotate from the z-axis from all the way vertically up to this direction OP. Okay? So we choose this direction because we have, once again, we have the z-axis, which is old, and this direction OP prime, which is new. Okay? So we rely on the old axis that's already there. So that rotation, and this rotation that you can see right here is actually always between 0 and pi. Okay? Because by the nature of this projection, if you think about it, so you have the P, you have P this point right here. Right? So if you want to do the rotation from the z-axis to this OP direction, this angle of rotation is always between 0 and pi. Okay? So you don't really have a large range as theta. So that's something we need to notice. But then that's pretty much everything. Except somehow we still need this distance r to somehow help us to describe the exact translation. So let me add that comment here. So we will require that phi angle is between 0 and pi. So a quick remark. We must have rho, the distance, to be non-negative. Theta is trying to decide that the vertical plane that's containing the point P. So it could have one period as the range of the angle, but phi is from 0 to pi, because within that vertical plane containing the z-axis, so that direction OP will be always in the upper half. Okay. All right, now to discuss more about the translation, note that so when we have that r there, we know x is r cosine theta and y equal to r sine theta, where r is the distance from the origin to that projection point P prime. Okay. So in the notes, you can refer to that figure from above. But here we're just gonna draw this again. So this is the z-axis, which is vertically up, right? So the point P is like right here. We have the distance rho and we have the rotation v, right? But then the projection down to the xy plane is gonna be somewhere like this. Okay, so that's the elevation is the z value, and this is p prime, and the distance from the origin. This is O to P prime. This is R, right? And that's this is 90 degrees. Okay, so this is exactly that the relationship within this vertical plane containing the point P and the z-axis, right? And if we want to look at it in a plane that's directly containing the z-axis and the OP direction, it should be OP prime direction. So that's what you see here. So the red edge and the dashed red edge, they form a right triangle. Okay, so that's P prime. That's P. This is the distance. The hypotenuse is rho, right? And here we just need to realize what that phi is. So this phi is the rotation angle, right? And we also know that this is also 90 degrees. Okay. Of course, the z-axis is perpendicular to the xy plane. So z-axis is perpendicular to the OP prime direction. Okay. And then it tells you what? It tells you the dashed line and the z-axis, they are parallel. So this angle is also P. Okay. So this tells you what? This tells you within this triangle, within this right triangle, R is the opposite edge, while the rho is the hypotenuse, right, of this angle theta. Okay. So this is D. So just recall that P has the coordinates x, y, z. Right. So we know that R, although we don't really want it within the description in rho, phi, and theta, but we can describe R, right? So R is what? R is rho times sine of phi, right? And observe that R is rho sine of phi. And at the same time, we realize that Z is what? Z is R, Z is rho cosine phi, right? Rho cosine. So Z is the adjacent edge, R is the opposite edge, rho is the hypotenuse, right? So now that's pretty much everything, okay? So we know, okay, now Z is described in terms of rho and V. R is determined also in terms of rho and V. And finally, we just replace this R into X and Y. So everything now is described in terms of rho, V, and theta. Okay. Hence, we get the translation here. So X used to be R cosine theta, right? But now R is rho sine phi. So we have X equal to rho sine phi cosine theta. And at the same time, Y equal to rho sine phi sine theta, right? And finally, Z equals to rho cosine. And also for the sum of squares, we do have nice sum of squares here. So we know that x squared plus y squared is r squared, right? R squared is rho squared sine p squared. And we can put down that along with z squared, right? Now z squared is rho squared cosine squared, right? So if you add them up, this Pythagorean theorem, x squared plus y squared plus z squared now equals to just rho squared. Okay. So indeed, you will be able to describe this sum of squares into a single expression. So these are the translations in the spherical coordinates. Any questions so far? So yeah, let's quickly look at an example. So we see now instead of x, y, z, we have now one distance and two angles. Okay, so that's one more angle comparing to the polar coordinates. Right? Example. So let's say we have the point which is in spherical coordinates. The spherical coordinate is 2, parallel 4, parallel 3. So just realize that here we have rho, theta, and phi, right? So that's the order that we describe this. That's the order that we describe this polar coordinates, spherical coordinates. So here, rho is of course the first entry of the tunnel, and then theta is the second, and then finally phi is the third. Okay. So just utilize the formula from above that we'll be able to translate, so that the rectangular coordinate is the point square 6/2, square 6/2, 1. Because x is, so rho is 2, right? So we just utilize the three equations on the left hand side. So it's 2 sine of parallel 3, cosine parallel 4. Just substitute, we substitute phi first, and then theta. Y is 2 sine parallel 3 times sine. Parallel z is 2 cosine. And then we just need to realize that sine of parallel 3 is square root over 2. Okay? Cosine of parallel 3 is 1. So that's 2 times 2 times cosine and sine of parallel 4, they're both square root 2. Okay? So these are special trig values for special angles that you probably want to be reminded of. Right. So this is translating from the spherical coordinates to the rectangular coordinates. So it's good. So these are formulas that are putting purple boxes are definitely important. Okay. And then if we want to translate from the x, y, z coordinates into rho, phi, and theta, so we still follow this logic. So let's say we have the point 0, 2 square root 3, and then 2. So somehow here we want to follow that order that we established this graph from at the beginning. Okay? So we want to find spherical coordinates, rho, theta. So of course, the first thing that we can realize is that rho is the distance from the point to the origin. Okay, so rho is x squared plus y squared plus z squared. And we always assume that rho is not negative. So we always choose the positive one. So that's gonna be easier for us in consideration. So we just we have 0 plus 12 plus 4. Okay. So the sum of squares. So it's square root of 16, which is 4. And then we just need to realize that z is rho cosine. Recall that z equals to rho cosine phi. So we have basically z is -2, right? And then rho is 4. And here we know that cosine phi is -1/2. And also we realize that phi is coming from 0 and pi. It's actually a decreasing function in that interval. So there's only one angle. Okay. So let me conclude today's lecture by saying that phi has to be 2 pi/3. Since phi is between 0 and pi, we must have need to be. So we are looking at the translation of the coordinates. Okay, so basically we have the rectangular coordinates 0 to 2 times 0 to 3 and -2. And we want to get the spherical coordinates. So we basically follow the order that we set up these parameters, rho, theta, and phi. Okay. So rho is the distance that's actually not so difficult. Phi relates to the z coordinate. So basically, what's nice about the angle phi here is that we know, okay, this is the rotation angle from that z-axis, positive z-axis to the direction OP that you have. Okay, so essentially, this phi is the angle cut between two vectors. Okay, so you rotate from one to another. So this phi is always between 0 and pi. So what's nice about the cosine function here on this range? So if you quickly sketch, cosine looks like this. Okay. From 0 to 100. So it's always a decreasing function on the entire interval. So as long as you get let's say this is -1/2, then that tells you, okay, there's only one angle that's associated to it. Okay. And that's the way that we find the angle P to be 2 pi/3. Okay. And then finally, we know we happen to use the x and y values. Okay. And then we know what rho and phi are. Okay. So based on the circle number and the box number that we can calculate, we're able to calculate cosine and sine. So these are the lines that I wrote from last time. Here, we're able to calculate that cosine of cosine of theta now must be 0 and sine of theta must be 1. So this is within the xy plane. Associating to the xy values, what's going to be the rotation angle starting from the x-axis to that projection location. Right? So then we know, okay, there's only one angle within the one period that's giving you these pair of values. Okay, so cosine theta equals to 0. So just by looking at the, if you want to complete the entire period, so there's going to be two angles. It's going to be pi/2 and 3 pi/2, right? From here and here within the small picture on the upper right corner. But then you also need to have sine theta equals to 1. So that's leaving us one solution. Okay, so that tells us theta must be pi/2. Since theta is between 0 and 2 pi, we have theta must be pi/2. Okay, so there's only one angle for that. So that leads us to the cylindrical couple. So spherical coordinate is basically rho here is 4. Theta is power 2. And B is 12. Any questions so far? So now, basically, these are translations. And of course, the essential topic that we want to cover is the triple integral over spherical coordinates, right? And then the only thing new is how we're gonna translate the volume. So so it's always the case that we start by rectangles on these kind of special coordinate system. So as long as we know how to subdivide a spherical rectangle, then we'll be able to write down everything nicely. So once again, we define this solid B that is a rectangle in spherical coordinates. Consider spherical let's say the box again. So the shape of this spherical box is going to be different from a traditional box, but it highly relates to a polar rectangle. Okay. We now just introduce one more element towards it. So we are looking at rho theta theta rho. And then here we just give specific bounds for these three variables. Okay. So let's say rho is between A and B. We have theta between two angles, let's say alpha and beta. And now let's say B is between two other angles, but now we just call them C and D. So of course we want to know, we want to give an illustration of the shape of this box shape in a spherical sense. So of course, make sure to utilize whatever programming language or website that you can utilize to plot it yourself. So that would be more accurate. But here we want to give a simple illustration and may not be super accurate. But the idea is not so complicated. Okay? So if you just remember these two, that's somehow. So basically, so if you have r and theta, that's actually not so bad, right? And we actually know in this three-dimensional space how we're gonna get that r from rho. So rho is the distance from the point to the origin, but r is the distance from the projection point in the xy plane to the origin, right? And then you do the rotation theta, it's gonna be sector. And then here, this p is actually rotating that the OP vector. Okay, so that's also so it's somehow interesting. So let's quickly take a look. So we look at the vertical plane that's containing that point and our z-axis. So basically, you're looking at the angle p. So we have a sector. Okay, so now let's say the point is here, and then from A to B is probably something like this. Okay. And then there's a circular sector. Right. So this is C and D. A little bit lower. And then from, let's say from this point to this point, we have a row between A and B. Right. And finally, we just need to do the evolution along the angle theta, right? So now just recall what that theta is. So theta is actually you do the projection down to the x-y plane and then do the rotation. So that's actually saying what? That's actually saying we're actually rotating around the z-axis. Okay. So let's quickly do that projection down. And that gives us a distance which is r, right? This is r. So this hypotenuse is zero. Just be reminded. And then now, so we're gonna do the evolution for this red dashed line radius. So because the theta is actually this angle, right? So it's gonna be increase from alpha to beta, okay? Alpha to beta. Okay. So that's the evolution here. And so there's gonna be another circular arc. And now, so basically, what's gonna happen for this black sector above, it will be somehow just be an evolution of so around the z-axis, okay? So you can somehow imagine that it will give you special arcs, but they are parallel. Well, they're kind of horizontal. Okay, so this evolution is horizontal in a sense. So let me just quickly sketch these edges. It's going to be something like this. So here I want to make sure that these are seen horizontal. Okay. Because that's the way that we do the evolution. Because we are revolving around the z-axis. And that's pretty much it. Okay, so now you see the shape definitely is a little bit different from before. Okay, so this is what we call a spherical wedge. Okay. So, and of course, when we try to subdivide this kind of solid into pieces, where we subdivide this interval from A to B, this theta interval from alpha to beta, and finally this phi angle from the interval C to D, then we're gonna create small pieces of wedges. Okay? So then the essential problem is basically given this kind of shape, what's gonna be the volume that's approximated for the subdivision. Okay? So then we're gonna So we're gonna utilize those facts. Let's say here this is gonna be a sector, but then we're gonna evolve around the z-axis. So there's another thickness, okay, that's resulted from the evolution. So basically we use the approximated area multiplying the approximated thickness from the rotation. So we're gonna do that. So essentially it's the same figure. So let me copy the figure down. So if you are doing a subdivision and we take a closer look, it's gonna be roughly the same picture. But we're just gonna be careful about the way that we approximate the volume. Okay. So now these are not that important anymore. So now we look at the increments. Basically, we have the so let's look at that again. So here, so the change in rho, right? You subdivide the interval of the distance from the point to the origin to be equal pieces. It's going to be delta rho. It's going to be, excuse me, it's going to be this side, right? So the increment of the distance is going to be delta rho, okay, that's that. And then if you do the delta phi is going to be the angle facing the section. So that's not so hard to see. This delta phi, right? And then what about delta theta? Delta theta is the rotation angle horizontally, okay? So around the z-axis. So that's exactly the angle. You can see from the previous picture. That's right here. That's between alpha and beta. Okay, so that's delta theta. Okay. And then now to approximate this volume. So basically for this volume, this is again related to the distance that it has from the origin and the rotation radius at the bottom. So we just need to realize what these are. Okay? So now for the sector, for the circular sector, this arc is what? This arc is actually rho times delta phi, right? So this is the arc that's facing this angle delta phi. Okay, so this is rho delta phi right here. Okay, so where rho is the radius from the origin to the point. Right. And finally, we just want to, okay, now we just recall that we do the evolution of the sector. Okay, so this sector, what do we do? So we rotate it around the z-axis. Okay, so in a sense, we need a thickness along this direction. Right? So how much is it? This is exactly this arc right here, right? So they are the same. And how much are they? So if you're thinking about it, basically when you do the evolution, if you want to establish that the distance from this point to the z-axis, that's exactly what you have seen from the bottom. Okay? So these are the exact same well, circular sector in a sense. Right? So basically, that tells you the distance here is actually that old r that we have seen. Okay. So this r is actually rho times sine of b. Okay. So if you go back to that projection picture, so basically the distance rho is incredible. Right? So this in that old picture, this is rho. This is z-axis going up. This is projection down. And we used to have the angle P right here, which is the same angle right here. And then we were drawing the opposite edge R, the adjacent is Z, right? So R is a rho sine theta, right? Z is rho cosine theta, right? So that tells you what? That tells you the purple arc, circular arc, is going to be this radius, little r, multiplying by delta theta, multiplying by the angle facing it. Yeah, I'm just gonna write a bracket and then dot it. All right. So that's good. So then we're gonna multiply the things. Okay. So we used to have this kind of sector that's actually just the black the black edge multiplying by the red arc. And now we have this evolution in the horizontal direction. So we're gonna multiply by the length of the purple arc. Okay. So that's the approximated volume of the subdivision. So this is black delta rho multiplying by the red one, rho delta phi. Okay, so that's definitely relating to the distance rho. Okay. And finally, we have even a longer expression, rho sine phi. And we can put the things together. So this is what this is. We have rho squared, okay, sine phi. And then delta rho, delta phi, delta t. Okay. So this gives us the way that we translate from delta rho phi theta into d rho d phi d theta. Right? Hence, the triple integral over the solid, which is the spherical rectangle. So this is going to be long, because if you think about it, we want to write down. So basically, so let's just follow the same order as this delta. Okay, so it's going to be we just do the translation here. So it's rho squared sine phi, and then d rho d phi d theta. And just be reminded to fill out the integrals. So theta is between alpha and beta. Phi is between C and D. Rho is between A and B. Right. So this is the translation of the well, this is the way that you describe this solid E, right? And then we have the solid E, we have dB at the end. But now for the substitution of f of x, y, z is going to be a little bit long, because now x, y, z we want to express those coordinates in terms of rho, theta, and phi. Okay, so that's the spherical coordinates once again. So just remember, this is rho sine phi cosine theta for x, rho sine phi sine theta for the y value, and finally rho cosine phi for the z value. Okay. So this is indeed a long substitution here. And here, this expression for the volume translation, that's very important. And let me change the color by putting it in that, so that's clear up. So thinking that. So now let's quickly look at an example that's motivating this setup. Okay. Example. you recall, we have that example, which is the triple integral over the unit sphere, well, over the unit block. That we have x squared plus y squared plus z squared holding to the 3/2 in the exponent of the exponential function with base e, right? So we're going to calculate this. So before, so here where e is the sphere, well, it's the unit ball, enclosed by the unit sphere. So now, if we want to translate into the spherical coordinates, it's actually not so difficult because now it's a unit sphere basically. So so theta is between 0 and 2 pi. P is between 0 and pi. So that's definitely fixed. And then the radius is just the upper bound is 1. Okay, so we have E to be the set of all tuples rho theta p such that, so now here, so this is definitely a rectangle, so in the order doesn't matter that much. So p is between 0 and 1, theta is between 0 and 2 pi, and p is between 0 and pi. Okay. All right. And then we just do everything translated to rho theta. Okay. And triple integral over the solid of this function. By writing it down, we can somehow expect that x squared plus y squared plus z squared now can be much more similar because that's just rho squared, right? So basically we write it out. So we're expecting rho squared in the bracket, and then whole thing raised to the power of 3/2. And then we just need to be reminded that we need to translate the triple integral in terms of rho p and theta. Okay. So here, let's we have the equation on the top. We just need to do that. So here, be reminded to put down the volume translation rho squared sine phi. Okay. And now let's just follow the same order. So this is d rho d phi d theta. So we actually know that for a polar rectangle, so the order actually doesn't matter, but then we just need to be consistent. Okay? So here, theta is between 0 and pi. I will put it on the most outer side. Theta is between 0 and 2 pi. Okay. P is between 0 and pi. And finally, rho is between 0 and 1. Okay. And that's it. So that's too much space. That's not really needed. So let me slide into that. Okay. So now, so far so good. Any questions? So if it's good up to this point, then the rest is something old, right? So this is the triple integral over rectangle. So the bounds are all fixed intervals. So here we can just split, okay? Because now we have a product of functions. So these parts, these are a product of the function rho. And this is easy to handle because now we have rho squared raised to 3/2. So that's essentially just rho cubed, right? And this cube is actually not difficult to handle because we have rho squared, the rho right here. And so that's a substitution that we can do. And then for the angle phi, it's just a definite integral. For theta, is integrating a constant 1, right? So we write it. Okay, so from 0 to 2 pi, from 0 to pi, from 0 to 1, just like I mentioned, the exponent now becomes rho, rho squared raised to 3/2. Okay. So that's exactly, you multiply by the exponent together, so this is rho cubed. And then rho squared. Sine v, d rho, dv, d theta. And now since they are products of functions, we can split. Okay, so this is the integral from 0 to 1 of e to the rho cubed, rho squared, d rho. Okay, that's the everything about rho. And then everything about v is from 0 to pi, sine v, dv, and finally for theta is from 0 to 2 pi, d theta. And then here, so if you want to do the u substitution for the first integral, it's fine. So you just here let u to be rho cubed. So du is 3 rho squared d rho, and then you actually know that rho squared d rho is just 1/3 du, and you just do the u substitution for that. Okay. So you see this will become the integral of e to the u. 1/3 du, right? So here, I want to write down the antiderivative of the inner function explicitly, because that's just 1/3 e to the rho cubed. Okay. And then we evaluate the rho equal to the lower bound and upper bound. And for sine function, it's the antiderivative is negative cosine. Evaluate at lower and upper bound. And finally, that's just 2 pi for the last one. Then we just plug in. So we have 1/3 e minus 1/3 e to the 0 is 1. Okay. And then negative cosine of pi is 1 minus. So negative cosine of 0 is just 1. So essentially 4/3 e minus 1. Oh, this is a pi. It's pi there. Don't forget this. And let me just put a pi at the end. Okay. So we have 4 pi times 1/3 times e minus 1. Okay. So that's good. So now as a comparison, you can see that using spherical coordinates for this kind of question is super handy. Comparing to cylindrical and the just iterated integral, that's complicated. Because here we see a radical of x squared plus y squared plus z squared. Okay? So if you have x squared plus y squared plus z squared, it's kind of a hint that okay, I probably want the distance from the point to the origin that you need to be converted. Okay, that's one thing that we can think about. And the other hint is that okay, we have a sphere, we have unit ball. Okay, so that's also indicating that it's possible to utilize the spherical coordinates. Okay. And of course, we want to look at more examples. So now find the volume of the solid that lies above the cone, z equal to the square root of x squared plus y squared, and below a sphere. So here x squared plus y squared plus z squared equals to z. Okay, so let's quickly look at the code. So basically, this if you look at this equation right here, this says what? This says okay, for the point x, y, z, the elevation z equals to the distance from the point to the z-axis, right? So this is just the sum of squares of x squared plus y squared. So this is the distance from the point to the z-axis. So you know the shape of the cone. X, Y, Z. So z equals to square root of x squared plus y squared. So here, let's quickly explore the radius and so, okay, so the one that I just sketched is able to think in a sense. It should be better. So basically, this is the distance, right? This is the distance from the point on the cone to the z-axis. Okay. So here, this distance has to equal to the elevation. Okay. So you see the shape. So if you're looking at this right triangle that's forming by this hypotenuse and the edges right here, this should be a equilateral right triangle. Okay, so that's the shape for the cone. Okay. And then for the sphere, we need a little more work because we can do computation of squares. So we have. So if we move everything to, on the left-hand side, we will have x squared plus y squared plus z squared minus z equal to 0, right? And then to get the radius and the center, we need to complete the square, right? So this is a negative z, okay? So we have a constant -1 here. And just remember, what we do is we use this -1 right here to divide by a 2 and then square and then put everything on both sides. So another way to write it is this is x squared plus y squared plus z squared minus z plus this is actually putting 1/4 on both sides. And z squared minus z plus 1/4 is actually a complete square. Okay? X squared plus y squared plus no, this is z minus 1/2 of x squared. On the right hand side is 1/2 squared. Okay. So this gives you the center and the radius. So now we see what? We see the radius is 1/2. The center is 0, 0, 1/2. Okay, so this is 1/2 units above the origin. So that's where the center lies. Okay. So if I want to get fixed here, so the largest circle, that's the elevation of the center. And this is diameter along the z-axis. Right. Y, X. Okay. So this is the center of the exhibit. So 1/2 is the z coordinate, and the radius is 1/2. All right. All right. So from the picture, you can see. Okay. So what does it look like? So the top of the solid here is this upper hemisphere. Okay. And the bottom actually is the cone, and then the cone actually goes through the circle right here. Right. So this is the circle because now the elevation is 1/2 and the radius is also 1/2. Okay. So you can somehow imagine these are coinciding. Okay. These circles are coinciding. Okay, so let's quickly put the figures together. So basically, we have a semi-sphere on the top. So that's and then the cone, the bottom, the z-axis, y-axis, x-axis, origin. Okay. So on the top we have the sphere once again. On the bottom we have the cone. right? So that's the illustration of the figure. But of course, here we want to go further by writing down the spherical description of the surfaces. Okay. And actually, that's not so difficult, but we need to be careful. Let us study the description of the surfaces under spherical modes. So here, instead of the geometric sense, let's just use the algebraic way. Okay, so we know the translation x squared y, which we know the translation x, y, z in terms of rho, phi, and theta, right? So we just study that. Do the substitution. Okay. For the surface c equals to the square root of x squared plus y squared, we have. So if you recall, z is what? Z is rho cosine phi. Okay. And now x squared plus y squared is actually r squared, right? R, and you know what r is. R is rho sine phi. And if you recall, we can get rid of the square root and the square because rho is non-negative and sine phi is non-negative also because phi is between 0 and pi. Okay. So that tells you. So we get rid of the square and the square root, and it tells you what? It tells you, okay, rho cosine phi must equal to rho sine phi. And here, if we divide both sides by phi, since that's always positive in the solid, the cone becomes cosine phi equal to sine phi. Okay. Cosine phi equals to sine phi. And actually, within the interval from 0 to pi, there's only one angle that's having this property. Okay. And but you can go even further. You can say, okay, now this means what? This means tangent equals to 1. Okay. So sine over cosine, and that's 1. So phi must be pi over 4. So 45 degrees. So which is something somehow expected from the figure, right? So you're looking at the figure. This distance is the same as this distance. So this is pi over 4. Okay, in the figure right above. And that's the upper bound of the angle phi, which is the rotation from the z-axis to the boundary of the cone. Right. So now let's look at the polar, the spherical description for the sphere. X squared plus y squared plus z squared equals to z, right? So we again do the translation. So z, we know what that is. So it's rho cosine phi on the right hand side. But the left hand side, the sum of squares, right? Sum of squares equal to rho squared. So now that's kind of straightforward. So this tells you what? It tells you if you factorize, so either rho is 0 or rho is cosine phi. Okay. And rho equal to 0 doesn't is something not interesting. Okay. So the equation of the sphere is rho equal to cosine phi. Okay. So now let's look back at the figure. So this one says phi must be pi over 4. Okay. And this one says rho must be cosine phi. Right? So that tells you what? Tells you. So basically, we do have bounds. Okay. So the distance from the point, from the origin to the point, cannot exceed cosine phi. And so that's the upper bound. So phi must be between 0 and cosine phi. This is the varying bounds. Okay, we have functional bounds. And then for this cone, so basically tells you the rotation here from the z-axis to the ray is always having an angle that's less than equal to pi over 4. Okay, so this gives you a bound for the angle phi. Okay. But then, of course, since everything is symmetric with respect to the z-axis, it tells you theta is fine. So theta has an entire period. So we can describe the solid quickly. Thus, the solid is can E equals to all the rho theta phi tuples such that, like I said, theta is cut between 0 and 2 pi, that's the entire period. We put down the phi later as in the middle as the interval from 0 to pi over 4. Okay, that's nice. But we put the rho in the most inner because rho relies on other things. Okay, so rho relies on phi. So this gives you the order that you describe the volume of the solid. Okay. So if you write down the volume, then this is just integrating on the solid, right? But integrating one. So if we put the things down, so let's quickly write down the integral. So we have theta between 0 and 2 pi. So the phi, the rho, and then we need the rho squared sine of phi. Okay. So always remember that. P is between 0 and 4. Finally, we have rho between 0 and cosine. Okay. And we're integrating 1. Right. So now this is the integral that we need to be a little bit more careful about. But I just want to quickly mention that, okay, we have a function rho squared sine phi, right? Okay, I mess up with the order of the description. So of course here theta is on most outer side. But as long as you get that corrected, then it should be fine. Theta it should be here. That's the way I do it. So this is the rho. Okay. So integrate rho first, and then phi and then theta. Alright. So systematically using integration from the inner to the outer. Yeah, so we don't really need to write down the integral anymore. So okay, the function we're integrating is rho squared sine phi. Now the inner is in terms of rho. Okay, so sine is a constant. Rho squared gives you an value of 1/3 rho to the 3. And then sine is multiplied, and then we evaluate as rho equal to 0, rho equal to cosine phi. And then copy down the outer two variables, evaluate. So this is you see that when rho is 0, you are not really getting anything. So this is 1/3 cosine cubed sine phi. Right. And now up to this point is going to be just routine. So here, the integral is in terms of phi, and eventually you will get rid of phi and you get a constant, right? And then integrating the theta constant on a fixed interval, then you just multiply by the length of that interval, which is 2 pi. So here, essentially, this is just going to be 2 pi over 3, multiplying by the definite interval in terms of phi. And cosine cubed sine, if you recall, this is actually a really traditional trig integration. And the trick that you do here is, okay, both of them have odd powers, so you can just do use up. So you can do use up for, let's say, u equals to cosine phi.
So make sure to write down the details for that. Okay. When u is equal to cosine, then u is negative sign, right? But then when you plug in the angles, then cosine is a decreasing function, so we'll have smaller upper bound when you do the translation. But anyways, here you can also write down the antiderivative directly. Okay. This is -1/4 cosine to the 4th. If you now realize, okay, this is actually kind of a derivative of the inner functions. Okay, so now of course, if you differentiate, cosine to the 4 gives you 4 times cosine to the 3 times the derivative of the inner, which is negative of sine. Okay, so everything cancels out. Alright, evaluate b equal to 0 and b equal to pi/4. And eventually, if you plug in, you will get simplification of parallels. So here cosine squared of pi/4 is actually this 1/2, right? And if you plug in 0, you will get a 1.